So you were asking me about why the temperature curve of the diode was linear, at least over the small region. And so this gets weird and this gets in depth. I can really simplify it easy up front and say, well, your question was, when you look at a diode curve, you see this horribly nonlinear thing that looks something like this. And you're wondering, how in the hell can you be linear on there? Right?
Right.
That was loosely the question.
Yes.
Okay. So, the region we're working in, first of all, is actually not in, so this is VBE, and this is collector current. So, the region we're actually working in is in this region somewhere, because right, actually, yeah, somewhere in here is about 0.7 volts for silicon. So the very, very easy question to your, or answer to your question is, this curve is at 25 C. Now, if temperature increases, I remember how to get this straight in my head. I've got my book by Streetman here. This is my semiconductor physics book. What happens is this curve compresses. So what did we see? We saw that at VBE versus temperature, T looks like this, with a slope of about minus 2.1 volts per Kelvin. So
you're saying that the curve actually changes due to temperature?
The curve changes due to temperature.
Well, so that was part of my question, is that I found a lot of generic curves that look like this, and then I thought to myself, isn't this dependent on the material and the temperature?
Yes.
Which I found it odd then that virtually every place I looked said that was this basically was the curve without controlling for those two variables.
Correct. So this is the curve at 25 C. So we get warmer, that means our voltage goes down, right? So as we get warmer, this curve still goes through zero here. It looks like this. And so for a given current, and as you get hotter, no, as you get colder, VBE goes up. So we'll do it this way. As you get hotter, VBE goes down. And as you get colder, VBE goes up. So what's happened is, if you hold current steady, so if you've got a current source up here going into your diode, so let's say that limits things to 500 microamps. You're always going to have 500 microamps going through there. That's what a current source does, right? Then this voltage here, so you're holding it stable here.
So
now what you're doing is sliding this curve back.
So you're measuring the voltage change?
Yes.
Okay.
Now, this is the simplest possible answer.
Okay.
To what you asked. We're not sliding up and down this curve. We're sliding the curve back and forth across here. And this is a fairly linear dependence in temperature.
Okay.
Now, the next part of your question, or the next question you had, was IS. What the hell is IS? And how do you measure it? So IS, so the diode curve is IC, which is this current going through the diode. For transistor, it's IC, but we're diode connecting our transistor, so it basically is a diode. So use an IC collector current, even though there's no collector per se on this.
Okay.
So IC is equal to IS times E to the VBE over NVT minus 1, right? I think that's what I said in the other video.
It sounds, yeah.
Where VT is the thermal voltage, which is generally at 25C, it's about 25 millivolts.
So is that a property of silicone, or is that just...
Well, it's it has to do with, because VT is equal to, I want to say it's Q over KT, going through, just trying to remember. And this is the elementary charge of an electron. So it's like times 10 to the negative 19th.
Okay.
And this is Boltzmann's constant, so it's 10 to the minus 23rd.
Okay.
And then T is your absolute temperature in Kelvin, 0 to whatever. So as your temperature changes, your VT changes, which is going to have an effect on the collector current. So what I was showing in the math was, well, as long as...
So that's a pure linear.
Yeah, except it's in an exponential.
Oh, yeah.
So that's this part of the curve. So as VB, or V across your junction changes, you're at an exponential current. What happens, though, is, so we'll talk about, think about this as 1, 2, 3, 4, piecewise, it's a piecewise linear type thing, right?
Okay.
It's a piecewise
Yeah.
function. So you've got a breakover that happens like right here somewhere. You've got another breakover that happens here somewhere. You've got a breakover there, a breakover here, and then another breakover there. So these are all your functions coming up. So this diode that you have has some resistance. V equals IR, V equals current times resistance. So as you keep increasing your VBE, you can't stay in this exponential. You start getting to the point where you start to become current limited. And if you look at a transistor curve, you've got, the foldovers, right?
Right.
And depending on how you've got it biased and all that other stuff. So you're out here starting to get in an ohmic region of space, of device operation. All right. So we call this ohmic, I guess, for lack of a better term. We call this exponential. And to simplify things, as long as we're like in this region, somewhere around 0.7 volts, if VBE is much greater than VT, then this simplifies to approximately IC equal IS E to the VB E over NVT. Approximately. Because this becomes the dominating factor and it always becomes E to the VBE and this minus 1. Because IS is actually pretty small. Now, you were asking, how do you measure IS? What the hell is IS? IS is this. This is IS. This reverse current. So if I take my diode and I hook him up to a voltage source, I guess. It doesn't matter. I'm going to just connect him through a resistor like this so that this is some positive voltage. And he's reverse biased. And in theory, In a perfect world, no current flows, right? Diodes conduct current.
Right, right.
Diodes conduct current this way, but not that way. Reality, some flows.
Right.
The amount of current that flows is Is. Is is a function of, if you look at the diode as being a block of stuff, and this side is doped P and this side is doped N, it's a function of the cross-sectional area, A. It's a function of the doping concentrations. So it's the band gap was in the thing, so the band gap's a part of this. And in here somewhere is the temperature. So at absolute zero, if you could ever get there, we would allege that no current will flow. There's no molecular motion. Electrons are generally stuck in their bands, and there's nothing to really make them move.
Right.
Anytime you're above absolute zero, you're going to start getting some drift currents going this way, and the warmer it gets, the more there will be. So this Is is also temperature dependent, and your IC is whatever this is multiplied by Is. So Is becomes the dominating factor. It's the multiplier on everything. So when you look at this thing, if you're really cold, you'll see that the curve, if you're really hot, this is the hot curve, right? If you're hot, the curve comes down like this. And if you're cold, on this curve, goes in like that, right?
Okay.
So what we're doing here to cause this to happen is bulk, because we're modulating Is. It's like I just said in the thing, when you solve this out and get the you get the equation. When you solve for VBE, you get VBE is approximately equal to, let's see, we take the log of both sides, and we divide IC over IS. So we get the natural log of IC over IS times, we got that, have to multiply that in VT, I think. Is that right? So when you look at this, you initially would say, if temperature goes up, then VBE should go up. And if temperature goes down, VBE should go down. Except that Is dominates. That factor there is what dominates the whole thing.
Okay.
And I think I said this in the other video. The rule of thumb is that for every 10 degrees C delta,
doubles, right?
Is is approximately a double. So that's a big effect compared to this little effect. So now, I promised you I had a couple other ways of looking at this.
So I also had the one very elementary question of, so you've got this in an Arduino and you're setting it up.
Yeah.
How do you actually measure that current? Like, where do you pull that current from?
Okay, I can't measure that.
Okay.
If I were I in a lab,
yeah,
I would set up a diode with a picoammeter. So I'd have a picoammeter here and a voltage source with a load on it, and I would measure it.
Okay, well, if you can't...
Were I the company who was making it,
okay,
I would know a priori that my cross-sectional area was this, and that on either side of the diode junction my diffusion of N and my diffusion of P was X and Y, and I would know my diffusion barriers, and I would know up front, before I even fabricated it, what it should be. And then, after I fabricate it, I would test multiple places on the wafer and see how far out of whack they were to that and get a max and a min. Because you're not going to get perfect doping.
Okay.
You know,
so let me ask you even more elementary question then. How then can you use your IS to measure temperature then? If you can't measure it. If you can't measure it.
IS, I'm using this change. I mean, IS is fundamentally the source of this big change.
Okay.
But I don't need to know what it is.
Okay.
I take so I have my measurement system here.
So IS is what's pushing your VBE, and that's what you're measuring is your voltage change. Well, what I just thought was odd, and maybe I just need to think about this a little longer, is that the voltage and this IS are not really linked.
They are. They're integrally linked. But it's like going to a gas station. I know that if I push on this pedal, I'm going to go faster in the car. And when I go to the gas station, I take this thing and I stuff it in this hole and I do something, because every now and then it runs out of whatever it is that makes me go this fast. I have no freaking idea what's in there. You could be pumping water in there. I wouldn't know the difference, except that I know the difference. What I care about is the relationship of my foot to how fast I'm going.
Okay.
And how far this needle is on my dashboard compared to when I've got to go put this pipe in my car.
Well, I just thought it odd because when I started reading about it, everywhere I read was explicitly making the statement that IS and the voltage were not necessarily related.
They are. If you stay at a specific temperature and you never move away from that, then they disassociate, right? Because you fix the temperature then. So when we go through our electronics classes and we do all these things, and we're designing a board or whatever, we're making an assumption of what the temperature is. So it's a pain in the butt, but one of the things you got to do is, for a good design, is you have to design your circuit, and then you have to go and look at what your expected temperature ranges are going to be, and say, does the circuit behave the same way at cold, and does the circuit behave the same way at hot? With digital logic, it's not a big deal because we're just using the switches. We're banging them in and out of here. We're way over here somewhere and way over here somewhere. So the change is going to be very little. Going to the analog world, where I'm used to working in, it can make a big difference on how your circuit operates. Because now you're shifting these curves, and what you're normally doing is running up and down these curves. And now my curve moved from here over to here, and that's affecting something further down the line.
Okay.
And it becomes important.
Okay.
And I have seen that rear its ugly head and cause us to have things not work on some projects before. And then you get into the whole idea of corner testing, right? You know, I have a temperature range here that can go here, but my input voltage could be here. You know, it goes from 4.8 to 5.2, and this could be 0C to 125C if we're talking, or minus 17 C, which is 0 degrees Fahrenheit for industrial circuits. And then you can add, oh, well, maybe I've got, my input to the thing can vary, between this voltage and that voltage. You start talking about corner testing. You've got to hit this corner. You've got to hit this corner. You've got to hit all the corners in your testing.
Right.
To say it works where it's supposed to work, and it works in all these different possibilities we can get. And that can be onerous and painful. So sometimes we wave our hands and say, well, it worked at this extreme, these two extremes together, and these two extremes together. Everything's fine. Well, I've been bit by that. So It's rare that you get bit by that. I've been bit by it. So, now what's happening over here is when you get over into this region, you're getting into the Zener region. And so the Zener region, all right, I'm going to try and do this in a way that I have my diode. I'm going to draw him 3 times. It's the exact same diode. This is a piece P, N, P, N, P, N. And here we have no voltage applied. Here we have him forward biased, positive, negative. And here we have him reverse biased. As an aside, this is something I learned a long time ago, the symbol of a battery. These things represent the plates inside the battery. So, it used to be you could look at this and say that's a 3-volt battery. Because each plate's generally one plate set's usually 1.5 volts. Huh. Nobody follows that convention anymore, but that's where it came from. For what it's worth. Okay, so we know that this is silicon, which is a semiconductor, which is a crappy conductor, but it's sort of a crappy insulator too. When we add the doping, if I look at, do you know band gaps drawings? I'm not real good at them, so pure silicon looks like this. This is your valence band, and this is your conduction band. And this is EG here, which for silicon is 1.12 or 1.2 electron volts, whatever it is. So when you add a dopant in, you're adding, our common ones are arsenic and boron and phosphides and things like that. So we end up with another band here that's the phosphorus, say. I don't remember which one's P and N, so bear with me. Don't take literally, maybe that's the boron, I don't know. And so what this does is, he's really close and we've added all these electrons, but since we're not at absolute 0, they jump up here to the conduction band. And so now we have an excess of electrons up here. Whereas before we might have had, 1 or 2 holes down here and 1 or 2 electrons up here. But now we've got a gob of electrons up here. And the N is the opposite way, right? We add our dopant material, which has an excess of holes here, and now this new energy level here donates holes down to this, and basically by sucking up all the electrons and saying, they're mine, you can't have them. And so now we have only a few electrons up here, but we've got a gob of holes down here. So here the holes are the majority carrier, here electrons are the majority carrier, and the opposites are minorities. When you put this together into a junction, you get this guy's band, his donor energy level aligns with this guy's donor energy level. Like this. And you get this kind of a thing going on. So if you look at this, here's what happened. If this thing is not connected to anything, it must be at equilibrium, right? It must be, period, end of story.
Right, okay.
So I've doped this, and I've got over here, on the P side, I've got an excess of holes. Over here on the inside, I've got an excess of electrons.
And that has to be perfectly balanced.
It has to be perfectly balanced. It doesn't matter what the doping concentrations are. They don't have to be the exact same amount. You can have a non-uniform diffusion region. So here's the center. If I look at the diffusion lengths, if you will, If they're perfectly doped, I'm going to have a curve that looks like this.
Okay.
Right. I've got ends. These minuses are going to. These electrons are going to come over here. These holes are going to come over here, and this is going to be neutral in the middle. But there's going to be less electrons that are going to be able to jump that gap over to the other side. But if I've got, say, a more highly doped p side than an n side than a p side, then I could have something that ends up looking like this, right? But in the end, this will be in equilibrium.
Okay.
If it didn't, it would generate electricity on its own, and we would have created. We'd be rich. Figure out how to do that, we'll be rich. So what's going on here is this band gap falls like this. Well, maybe not that steep. Like this. And nothing flows. Now, from a point of view of what's going on in here, like I said, these things, thermal energy excites them. Electrons jump from this side to that side and recombine with holes and become effectively neutral. And there's what's called the diffusion length, which is part of carrier lifetime and some other things. So I'm a hot little electron and I need to do something, and I'm gonna jump over here to this neighbor. Well, I can keep going so far in a certain amount of time. So that's my diffusion time, and my lifetime is a statistical probability that I'm going to get trapped by a hole and stay there. So diffusion speed and diffusion time give a diffusion length. They're both statistical, they're both sort of averages. You know, some will be going a little slower, some will be going a little faster. But what you end up is with a diffusion length right here. So this part of the diode is effectively neutral, and you've created a barrier region there. Now, when I forward bias this, what I'm doing conceptually is I'm pushing positive here and negative here. These holes want to run away, so this region gets narrower, and all my holes are going to be bunching up here, right? Those are E's. And my electrons are going to be bunching up here because they're going to be repulsed by the charge coming in. So I'm narrowing this junction, which in the band diagram, I believe, flattens it out. Sound horrible with band diagrams. So this becomes closer to level, so that electrons and holes can just flow their different ways without having any obstruction in them. And if I forward bias it enough, then these guys are just going to jump right across and bang, they're going to go because their diffusion length is longer than this depletion region. And so they can diffuse across and go. And if I keep forward biasing it enough, we effectively, conceptually squish this all the way flat where there's almost nothing there and everything goes across. In fact, if we put a big enough voltage across it, push them the other way and then bad things start to happen. You're getting up into this ohmic region, and eventually you're going to burn the thing out because the heat's going to... In the reverse region, in the reverse bias region, you've got exactly the opposite, right? I'm putting a negative charge over here and a positive charge over here. So all my holes are going to come gather over here, and all my electrons are going to come gather over here. And I've effectively widened this gap. So it's come apart. There's a device called a varactor, which is a, it's a varactor? It's a diode that is made, this is effectively a capacitor.
I was wondering that.
That is effectively a capacitor. And in a lot of our electronic circuits, like a FM tuner or TV tuner, the way they're doing the tuning is by changing a voltage, which changes the width of this, and you change the capacitance on the filters.
So when I was going through this, I noticed that they talked a lot about an electric field, which is just like a capacitor. So I started thinking about it. I didn't think very long, but
yeah. So here you've got just a small electric field that's natural, but it self-cancels on either side. Here you're putting an electric field. E goes in the direction of electrons, right? So you're putting an electric field this way. Actually, no, I guess you're putting it this way. Oh, frick, I don't know. The electric field is squishing it together. Here, you're pulling them apart so that they don't want to go across, but at the same time, you're increasing the electric field, which is going to try to force them across. You're getting a whole bunch of P over here, or, it's going to try and push. Eventually, something's going to collapse. And what happens is, in the band diagrams, this gets steeper and steeper. But what you've got here now is a place where an electron can tunnel over. So we get quantum tunneling effects. And this electron can just hop right over to that side, because that's actually easier than jumping up into this band or any of the other things. So then you get reverse current flow, and now you're out here in the Zener region. And the neat thing about the Zener region, a Zener diode, is one that's made to operate right there, and they tune them for a specific voltage. You get a very, very small change in V for a very large change in current. It's a voltage regulator. It's not a great one, but it's good enough for a lot of things. It's good enough to be a stable reference for a voltage regulator, as long as the temperature doesn't change too much. And then if you get far enough along on this guy, the electric field gets so high, you basically collapse these things on top of each other. And now you go into an avalanche mode, which is down here. And in that, it's not the tunneling effect that causes the current. Well, it is, but what happens is that the electric field is so high, one of these guys jumps off into here, and when he does, he impacts another atom and knocks another electron loose. So for every one that comes across, two come out. Well, and of course, the same thing's going on the other side. Holes are going the other way, so it reaches an equilibrium, but now you're really pumping a lot of current through this thing, and now you're way down here somewhere. And currents can get really high, and avalanche photodiodes are made to do just that. One photon comes in, and you get a million electrons out, or a large number of electrons out. It's a way of amplifying your signal. And as long as that's just for a little pulse, no harm done. The heat goes away, and we're good. But if that keeps going for a long time, bad things happen. So this is sort of what's going on these different parts of the curve here also, which is not what you asked, but it was alluded to by what you asked. Yes, no, maybe?
Yeah, yes.
Does it make sense? Sort of?
Sort of.
Any more questions?
Not yet.
Not yet. Later day?
Wait an hour.
Wait an hour? All right.